All right, so we're going to start chapter 7 right now and take a look at what it's all about. Now, chapter 7 is about one single idea, and that single idea is called the central limit theorem. Now, the central limit theorem is a really big idea, not just in this chapter, but also it's the motivating tool, it's the machinery behind what comes in chapters 8 and 9 and 10 and 12. So it is the machinery behind all the stuff that we're going to do in the future chapters. So this is the reason, this central limit theorem, not only is it the motivation behind what we're going to do in the next chapters, but it's the reason why we study the normal curve so much. All right, it's why the normal distribution is important. Okay, again, I think I mentioned this in the last chapter. The normal distribution is a very common one, but it's not the only one. If we looked at chapter 5, there's lots of other distribution shapes. The reason the normal curve is important is because of this central limit theorem. So let me kind of explain what the central limit theorem is doing, and then we'll take a look at, well, what kind of calculations and inferences can I make via the central limit theorem. So let's take the set of data, which is just all the numbers 1 through 7. So 1, 2, 3, 4, 5, 6, 7 are in my set. And if you do a simple calculation, you'll find that the average is 4 and the standard deviation is 2. In fact, it's 4 even and 2 even, 2.00, 4.00. Now, one thing about this set is that if you drew a histogram or a relative histogram, what I have here, what we would see is that given the probabilities, we have a histogram which is clearly not bell-shaped. Okay, every single number, if I pick a number at random from that set, every single number has a 1 in 7 chance of being picked. So if I create the, again, relative histogram, it's completely flat. So obviously, it's not normal. However, what I can do is I can take that group of 7 numbers, 1, 2, 3, 4, 5, 6, 7, and instead of looking at picking a number individually, let's say instead of picking a single number out of that set, I chose 3 numbers. Now, there's a lot of different ways to get 3 numbers out of the set. I could have found the numbers 1, 2, and 3. I could have gotten out the numbers 1, 2, and 4, 1, 2, and 5. These are all ways to choose 3 numbers out of that set of 1, 2, 3, 4, 5, 6, 7. And if you count these all up, there's 35 different ways to choose 3 numbers. So again, take a step back. If I'm picking a single number out of that set, I get a flat histogram. If I pick 3 numbers out of that set, well, what can we know about these 35 sets? One natural thing would maybe to do is to look at the average of each of those subsets. Each of these 35, what's the average of the 3 numbers? So for instance, if I take the numbers 1, 3, and 7, I'd say, well, that's 11 divided by 3. So 11 divided by 3 is 3.66 or 3.67, rounded to 2 decimal places. So 137 has an average of 3.67. Now, if I did that for all 35 sets, the averages are going to be like this. I'm going to get one set having an average of 2. That set, by the way, I've matched these up 1, 2, 3. That's the first row, first column here. The average of 1, 2, and 3 is 2. Again, first row, first column. And then you look at all of these numbers. So here are the 35 averages for my 35 different sets. Notice that while the average of 2 occurred once, the average of 4 occurs a few times. 3 occurs multiple times. 5 occurs multiple times. 4.67 occurs multiple times. And so all of a sudden you get a higher frequency of certain averages and a lower frequency of other averages. Now, if you looked at those averages, again, these all came from the sets of size 3, and you created a probability distribution, this is what it would look like. So the averages, if you go back to that previous slide, were 2, 2.33, 2.67, 3, 3.33, 3.67, and so on and so forth. So they go from 2 to 6. The middle number here is 4. That has the highest probability. And since there's 35 different sets, we see that 2 occurred 1 out of the 35 times, 3 occurred 3 out of 35 times, 4 occurred 5 out of 35 times, and each one of these occurred those same numbers. Now, what would that look like for a histogram? Turns out it would look like this. So whether I did a relative histogram using probabilities or just a histogram using frequencies, it looks like this. And all of a sudden you see that this thing is kind of starting to turn into a bell-shaped distribution. So if I look at the averages, I get a bell-shaped distribution. Now, I hope that you can clearly see that this is symmetric. And I hope that you also see, since it's symmetric, that middle number is going to be the average. So it's going to be sort of an average of the averages, which in my case is 4. And also, well, if you think about the standard deviation, it turns out the standard deviation is smaller using the sets of size 3 than just by picking a single number individually. So this is the notation we use. We say that in this probability distribution, the average sub x. Now the sub x means the average of the averages. So the average of the sets is 4. And the standard deviation amongst the sets is 0.94. So the average of the sets was the same average as if we were picking an individual. The standard deviation has changed. So that's the big idea of a central limit theorem. Now, my example wasn't quite perfect because I didn't have a gigantic population to choose from. I only had this set from 1 through 7. So I didn't have a huge population to choose from, and I took subsets of size 3. So this one doesn't perfectly capture the central limit theorem, but it gives you kind of an idea of what's going on, all right? These sample averages turn out to be bell-shaped. If I had sort of a perfect idea of what's going on example, the numbers would just get too big. And so that's why I skipped that. So here's the big idea. I start with a huge population, like everybody in the state of Michigan. And maybe I look at their heights. And maybe I find out that the heights of people in Michigan are not normally distributed. But if I take samples of people and I treat those samples as what I'm looking at instead of treating the individual as what I'm looking at, the sample averages will be normally distributed. So while the original data may not be, the averages will be. All right. Now, that's based on a condition that we'll talk about in just a moment. So here's the central limit theorem. Here's the definition. It says if we take large enough samples from any distribution, no matter what kind of distribution it is, the averages of the samples will be normally distributed, and moreover, the average of my samples will be the average in my original distribution. And my standard deviation of the samples will be my original standard deviation divided by the square root of n. Now, n, again, is my sample size. So if I took samples of size 30, I'd say, well, my old standard deviation, my original standard deviation, divided by the square root of 30 is going to be my new standard deviation. Hopefully that makes sense. So we're saying while I won't be able to necessarily find the probability that one individual is between two values, I might be able to use the normal distribution to find if a group of 50 people have an average between those two values. So this allows me to connect the idea of samples and the sample averages to the original population average. And that's why the central limit theorem is so powerful. Now, you'll notice that I have large enough with an asterisk there. What I mean by large enough can mean one of two things. First off, if my sample size is bigger than 30 or equal to 30, then we can apply the central limit theorem. The sample size will be large enough as long as we sample at least 30 people. The second thing that could happen is you can actually sample less than 30 people if your original data is already normally distributed. So if your original data is normally distributed and you take a sample of 10 people, then you can still apply the central limit theorem. So no matter what your data looks like, if you have 30 or more people, the central limit theorem will work. If you have less than 30, then the central limit theorem will only work if your original data is normally distributed. And don't forget what the central limit theorem is saying. Once again, it's saying that while I can't look at individuals, if I take samples, their sample averages, the average of the sample averages, will be my old average, my original average, and my standard deviation of the samples will be my original standard deviation divided by the square root of n. So let's do some examples of the central limit theorem and see how we would use this in real settings. Okay? So if you look up the CDC data, The average weight of adult females in the United States is 168.4 pounds with a standard deviation of 45 pounds. Now, notice that who knows what the distribution looks like? It's probably not a normal distribution. If you can imagine weights of females in the United States, there's probably, it's probably all over the place, and who knows what a distribution would look like. But what we can do is we can say if we sample 30 females, what's the probability that their average, so the average of those 30 females, comes up between 150 and 175? So here's how we do this. We scroll up, I'm going to scroll up to this example that I just said. And we say, well, what are we asking? We're asking, what is the probability that something, in fact, we know what that something is, that something is a sample average. What's the probability that a sample average, so I'm going to call that X bar, comes out between 150 and 175? Okay, that's what we're trying to figure out. Now, in this case, we can use the central limit theorem. Why can we use that? Well, we said we're going to sample 30 females, and 30 is the cutoff point. Anything 30 or more, we know that the central limit theorem will apply. So if we take samples of size 30 or more, we know the central limit theorem is going to apply. Moreover, since we can use the central limit theorem, we know that these samples, let me go ahead and use the correct notation. So these samples, which are going to have an average, which is the same as my old average. So I look up to, what's my original average? My original average is 168.4. And, moreover, the standard deviation on this curve, on the curve of the samples, is going to be 45 divided by the square root of 30. Everybody remember that? So it's just as a reminder, what we said, what the central limit theorem tells us, is that if we take samples that are large enough, in this case, 30 females is a large enough sample, then our sample averages are going to be normally distributed with a mean, which is the same as my old mean, same as my original mean, and a standard deviation, which is my original standard deviation divided by the square root of n. Okay? So what's that tell us about this probability? That says, well, now I know that we're normally distributed. So to find probability, I can use a normal CDF function, just like I did in chapter 6. The lower bound is 150. The upper bound is 175. Now, the mean and the standard deviation are the mean and standard deviation from the central limit theorem. So my mean is 168.4, and my standard deviation is going to be 45 divided by the square root of 30. All right? So that's how we utilize the central limit theorem. So When you calculate this, by the way, I haven't typed it in yet, but I will. You can type it in with just writing in the square root of 30. So some people often think like, oh, I need to figure out what 45 divided by square root of 30 is. You don't. You can just leave it as 45 over square root of 30 in your calculator and get it like that. So what we would say is that this probability comes out to 0.7765. So basically, if you sample 30 females, you have about a 77 or a 78% chance that those 30 females have an average weight between 150 and 175. Now, let's do another one of these questions, and I'm just going to keep on this page right here. If we sampled 100 females, how would our problem change? So if we were to sample 100, well, clearly, once again, 100 is plenty for the central limit theorem. So we can use the central limit theorem once again. And oftentimes you'll see me just write CLT, right? CLT for central limit theorem. 100 is definitely a big enough sample size. Anything that's 30 or more will work, always. And then if I have original data that's normally distributed, then I can work with any n. So here's what we do. We can use the central limit theorem. Now in this case, when we sample 100 females, well, the average of samples of size 100 will still be my original average. It'll still be 168.4. However, the standard deviation of the samples of size 100 will be 45, that's my original standard deviation, divided by the square root of 100. So there's not a whole lot of change here other than, again, I'm asking the same question, what's the probability that we get a sample average between 150 and 175? We'd say normal CDF, the lower bound is 150, the upper bound is 175, the average is 168.4, and the standard deviation is now 45 divided by the square root of 100. When you type that into your calculator, you're going to get 0.9287. So there we go. We can use the central limit theorem, and basically what it does is it says, well, if we take our standard deviation, our original standard deviation divided by the square root of sample size, we can talk about the standard deviation of how the samples will be distributed. What's going to happen if we have 1,000 females? Well, if we have 1,000 females, we're basically going to do the exact same problem we just did, but instead of with 100, we're going to use 1,000. So we can still use the central limit theorem because obviously n being 1,000 is plenty big. It's well over 30. My sample average is going to be 168.4. I shouldn't say that. My average of the samples, not my sample average, but my average for the samples will be 168.4. My standard deviation for the samples will be 45 divided by the square root of 1,000. When I go to find the probability of my sample having an average between 150 and 175, lower bound 150, upper bound 175, my average is 168.4, and my standard deviation is 45 divided by the square root of 1,000. Now, by the way, hopefully you know this on your calculator, but if you just hit the second and then the enter key, it will pull up what you just wrote. So second enter is like a copy paste of what you just did. And so if you already wrote normal CDF 150, 175, 168.4, and then 45 divided by square root of 100, you can just put second enter and change your 100, in this case, to 1,000. And what you'll find out in this scenario, rounded to 4 decimal places, it turns out you get 1.000. In other words, it is pretty much guaranteed that if you take a sample of 1,000 females at random, that their average is going to be between 150 and 175. Now, it's not a perfect guarantee because in actuality, if you rounded it to more decimal places, you should see on your calculator that it's not always 999, but rounded to 4 decimal places, it is between 1.0000. Now, before I move on, I just want to point out what happened here. We were looking at weights of adult females in the United States, and we said, well, if we sampled 30 of them, the chance that we get between 150 and 175 as the average of the group is 0.7765. And if we sampled 100 of them, the average of getting between 150 and 175 went up to almost 93%. And if we sampled 1,000, the probability went up basically to 100%. So what's this telling us, or what's one way to view this? Well, notice that the average being 168.4 falls in between here. So one way to think of this is to say, as you start sampling more and more people, or any individuals, the chance that you'll get something close to the actual average of the population grows. So if you sample 30, you have a pretty good chance of getting something that's close to the average. But if you increase your sample size, it's going to be more likely a good representative for the entire population. So the bigger my sample gets, the better representation of the entire population it will be. So that's what we're seeing in this example now, going from about 78% to 93% to 100%, shows that as the sample sizes increase, you're more likely to get closer to the actual population average, which in our case is 168.4. Let's do another problem. Let's do example 2. What I would like you to do is take example 2, read it, and try to apply the central limit theorem to this one. Now, I want you to be very careful to look and say we are assuming that the original variable is normally distributed. Okay. So go ahead, read this problem, try to do this question, and if you get through with that question, you want to try the next 2, go ahead and try the next 2. Oh, I'm sorry, try the next 1. So go from 10 males to 40 males. Push pause on the video, try it, and then I'll come back and do it. All right, so hopefully you did that, and hopefully everything worked out right. So when you're doing these problems, first off, the first thing we should do is to identify the average and identify the original standard deviation. So what this is saying is that the average testosterone level for this age group of men is 546, that's like nanograms per deciliter or something like that, with a standard deviation of 133. So the average is 546, and the original standard deviation is 133. Now, our question says if we sample 10 males within that age group, what's the probability that their average comes out between 4 and 500? So let's go ahead and do this. First off, you might say, we have 10 males. 10 is too few of a number because we know that our central limit theorem needs to have 30 or more to work, right? But not all is lost because we have this other addendum that says, well, we can use less than 30 if our data was already normally distributed. And sure enough, we're assuming that the original data is normally distributed. So we can use the central limit theorem, and by the way, on the test, I'm not going to give you one that you're not going to be able to use the central limit theorem on. So just FYI. So on the test, I'm not trying to trick you. I'll say, hey, what's this? So we can use the central limit theorem because the original data is normally distributed. Now, when we do that, I'm going to copy and paste just so I don't have to type in everything again. When I do that, we see that the average of my samples of size 10 is going to be my original average, 576. That's what the central limit theorem says. My standard deviation is going to be my original standard deviation, which is 133, divided by square root of my sample size. So we're dividing by square root of 10. Now the question asks, what's the probability that we get between 400 and 500 as the testosterone count for for a randomly selected average group of 10 males, or males that age, maybe I should say that. So what would that be? I'm sorry. Put that into your calculator as normal CDF, 400 up to 500. My mean is 546. And my standard deviation in this case is 133 divided by the square root of 10. And how that comes out on my calculator is 0.1368. So what that means is that if I take a random group of 10 males, the probability that that group has an average testosterone level between 400 and 500 is close to 13 or 14%. So that's what we're asking. Again, anytime we're dealing with selecting a group of people instead of an individual, we're really talking about the central limit theorem. Well, in this class, that's what we're talking about when we're using the normal curve. So let's take this next one. If you haven't done this yet, go ahead and pause the video and do it. Otherwise, just keep going. All right, so hopefully you did that. Again, here we sampled 40 males, so I don't even care if the original data was normally distributed or not, but it is, so it doesn't matter. So we can use our central limit theorem. We have a big enough sample, and we kind of satisfy both conditions. We have a big enough sample, and my original data starts out as normal. So in this case, I'm sorry, I'm going to just say n equals 40. There we go. So in this case, my average of samples of size 40 is going to still be 576, which is my original average. And my standard deviation of the samples of size 40 is 133 divided by the square root of 40. Okay. So if I ask the same question about samples of size 40, well, what's the probability of getting that group having an average between 400 and 500? The testosterone level being between 400 and 500. All we would do is say, well, our lower bound is 400, upper bound is 500, my average is 576, and my standard deviation is now 133 divided by the square root of 40. And all of a sudden, the chance that you get between 400 and 500 as the average testosterone level in the group is 0.0144. So we see that the probability in this case, as my sample got larger, the probability went down. Okay? Now, there is a reason for that. Remember in this previous case, I said, well, 168.4 was between 150 and 175. So as the sample size grew, we were getting more samples which were close to 168.4, which were close to our average. And so since my probability range included the average, the probability was going up. More samples getting close to the average means there's more stuff between 150 and 175. Well, the same thing is going on here, but in this case, notice that my average is 546. So as more stuff gets closer to 546, that means less stuff is going to be between 400 and 500. So because the average is not in here, less stuff is going to be there. Let me kind of explain what I mean by trying to draw a fairly crude picture, okay? So let's pretend I took a sample of size 10, all right? And I know that samples of size 10 form the blue normal curve that I just drew, okay? So samples of size 10 form this blue normal curve. We know that if I do samples of size 10, the average is going to be right here in the middle. Well, what we're saying is if you do samples of size 40, what's going to happen is more stuff is going to be towards the middle. So it's still going to be a normal curve, but it's going to be a normal curve which does something like this and has more stuff in the middle and less stuff on the outsides. This is fairly poorly drawn. Let me undo that and try to redraw it a little bit better, making it look a little bit more like a normal curve. Something like that, okay? So more stuff goes in the middle, less stuff on the outsides. So if I'm looking for some type of area to the right, well, as we go to the right, or let me put it this way. So when n gets larger, more stuff is going to be in the middle. More stuff is going to be closer to the average, and less stuff's going to be on the end. So if my probability includes the average, as the n goes up, I'm going to get a bigger area. As if the probability I'm looking for does not include the average, so for instance, let's say the probability I'm looking for is something like to the right of this black line, then what's going to happen is as we go up, as our sample size goes up, more stuff, less stuff is going to be to the right of that black line. Hopefully I explained that. But basically, more stuff's getting pushed towards the average as your sample size goes up. So if I say, well, what's the probability of getting closer to the average? Well, your probability is going to increase in that case, as long as your average is included in the probability you're looking for. If the average is not included, then the probability is going to go down. Hopefully that makes sense. If it doesn't, it's not a huge deal that you know that, but basically all I'm trying to say is that as the sample size goes up, more of the samples are going to have an average which is close to your original population average. Okay, so let's do another example. And we're going to do the life expectancy example. So what I'd like you to do is read this life expectancy example and try to answer a question about the probability that the average lifespan is over 80 years, and do that with both 50 people selected at random and 500 people selected at random. So push pause on the video, read the question, and try to do this on your own. All right. Hopefully you did that. And what our take on this is, or what this should be, is the same thing we've been saying. Well, here we're surveying 50 people, and we could imagine that probably life expectancy, the lifespan of people originally might not be normally distributed. You know, most people die at older ages, and then there's all kinds of peaks and valleys. So probably our original data is not normally distributed, but we can still use the central limit theorem because our sample size is 50. And as long as our sample size is bigger than 30 or equal to 30, we're fine. So we take a sample of people and we're saying what's the probability that that sample's average lifespan is more than 80 years. So sample of 50 people. Well, all samples of size 50 are going to have an average, which is 78.74, our original average. And our standard deviation in this case, the standard deviation of the samples, is going to be our old standard deviation, which is about 15, divided by, in this case, the square root of 50 because that's my sample size. So it says, what's the probability that the average of this group is above 80 years old? So you use normal CDF. Your lower bound here is 80. Your upper bound just needs to be a really big number, maybe 100,000. 100,000 would be a really extremely long life. But again, we just go to some really, really big number. Our average is 78.74, and our standard deviation is going to be 15 divided by the square root of 50. So I just have to type that in on my calculator, which I have not done yet, so I'll type it in right now. And once I typed that in, I got that my probability of this group having an average over 80 years old is about 0.2763. Again, hopefully you got that same thing. If you didn't, either you typed it in wrong or I typed it in wrong. Hopefully you didn't do that. Now, what's going to happen when we sample 500 people? Relatively the same thing. We say we can use the central limit theorem. N is plenty big enough. 500 is well over the 30. The average is still 78.74. The standard deviation now is going to be changing to 15 over the square root of 500 because I have a sample of 500 people now. The probability, again, we're trying to find what's the probability that the average is going to be greater than 80. So we're going to use normal CDF, 80 up to really big number. My average is 78.74, and my standard deviation is that 15 over the square root of 500. Okay. Once again, on your calculator, you should be able to hit second enter, and the only difference between this first part of the problem and the second part of the problem is that we went from 50 to 500. Once you do that, what you'll see is that the chance that that group has an average life expectancy over 80 is quite lower. It's about 3%. So again, we're trying to find probabilities. We're using normal curves. But instead of just picking one individual at random, these central limit theorems are always treating the sample as a group in and of itself. And we're not talking about the individuals inside the sample. We're saying, well, what's the chance that that sample has a sample average which is bigger than 80? All right, one more example. Let's take student loan debt. All right, I want you to read this and try to answer this question. And then once you've done that, just change the 40 to 200 college graduates. So go ahead, read it, answer the question, push pause on the video, and then come back and see if you did it right. All right, hopefully you did that. Once again, instead of looking at individuals, I'm dealing with groups we're doing a sample of 40 college graduates. So anytime I'm talking about a sample and a 40, and we're talking about what's the chance that that sample has an average debt, which is less than 30,000, that's right for the central limit theorem. So, how do we do this? First off, we can use the central limit theorem, and we all know why. We have our sample size, which is bigger than 30, or equal to 30. In this case, sample size is plenty big. Sample is 40. Now, all of the samples, all of the different samples of size 40 we could get, the average of those samples must be 37,172, which is our original average. And of all the samples of size 40, our standard deviation has to be 14,600 divided by square root of 40. Now, be careful here. We're saying, what is the probability that a randomly selected college graduate has less than $30,000 in debt? So we're going to, again, we can use a normal CDF because we're using the central limit theorem. We're going to take a really big negative number, like negative a million, and then take our high number as 30,000, and then put in the average, which is 37,172, and then put in the standard deviation, which is 14,600 divided by the square root of 40. Now, here's what I did. When I typed that in, I got something that looked like 9.4559 blah 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 e negative 4. So what I got there is scientific notation. 9.46 times 10 to the negative 4th. So let me write that as times 10 to the negative 4th. On a test, you can write that. That's perfectly fine to write on a test, 9.46 times 10 to the negative 4th. If you came up with something like this on the Moodle homework, what I would have you do is type in like 9.46 into one box times 10 to the, and then in the exponent box, put a negative 4. So it would look like scientific notation if one of your answers actually did come out as scientific notation. All right. Knowing that, I want you to go try the next problem. What if we took our sample, I apologize for this, and instead of making it a sample of 40 college graduates, what's the probability that we sample 200 college graduates and their average comes out less than 300? Or is it not, sorry, not 300, 30,000. All right, so hopefully you went ahead and did that. Stuff is going to look very familiar. We can use the central limit theorem because n is plenty big. It's over 30, it's 30 or more. The average of all the groups of size 200 is the same as my original average, 37,172. The standard deviation of all the groups of size 200 is my original standard deviation, divided by the square root of 200. So that means the probability of having a single sample of 200 college graduates and having their average being less than 30,000, we would do normal CDF, negative big number, up to 30,000, average, and then original standard deviation divided by the square root of 200 is my new standard deviation. And once again, my calculator gives me scientific notation. You should have ended up with 1.88 times 10 to the negative 12th. So that's what the central limit theorem is all about. It's saying that if we can't apply the normal curve to an individual, so I can't say, well, my data is normally distributed originally, then I can get around that by taking sample sizes. And we know samples, as long as they're big enough, their averages are going to have a normal shape. So I can use the normal shaped, the normal distribution to understand probabilities of sample averages. And like I said, this is a big deal. This central limit theorem is an enormous deal because, again, we all know that not everything is normally distributed, but what we just said is essentially, while original data is not always normally distributed, sample averages are, as long as we take big enough samples. So hopefully that all makes sense, and that is the end of chapter 7.